therefore the proof of the signature theorem is that any of these any k genus gives rise to a ring homomorphism. So let's look with what we have here. So suppose we are starting off with this oriented Cobordism ring, and this maps to the rational numbers. So if we pick any of these manifolds in this ring, then we can think, well, thinking of k genus as a function, then this maps to this here, and that is a rational number, so it's in here. So we have that map, and this induces an algebra homomorphism that we have here from this tensor product to Q. That's very important. And also very important are these relationships that, as we'll see in a while, these relationships are very similar to some properties of the signature theorem, of the signature. Well, now here we have our first definition of the signature. What is the signature of a manifold? Well, we are considering a compact oriented manifold of dimension m, just as we have there. Then the signature is defined as follows. If we have a manifold with dimension not equal to 4k, then we are safe. The signature is 0. If it is equal, if it's a 4-dimensional manifold or 8-dimensional manifold or so on, or k-dimensional, then by definition the signature is the signature of the intersection form. Well, but what is an intersection form? So we have to define that first. So, well, an intersection form, we have the definition here. An intersection form is just a type of a non-singular symmetric form over R. So we look at our definition of symmetric form that I've written down up here. Well, a symmetric form is only just a finitely dimensional vector space and a bilinear pairing, as you see here. Lambda is the bilinear pairing. Our k's are here finite dimensional vector spaces, so we have this map. And in particular, the intersection form of a closed 4k dimensional manifold is this non-singular symmetric form over R. Here, our k has become the cohomology group dimension 2k of this manifold over R. And our bilinear operation lambda has become this operation here. So when we apply lambda to the pair xy, it's going to give us the cup product of classes, of cohomology classes in this group. Well, this cup product is going to be evaluated against the fundamental class. So that's what our bilinear pairing is going to give us. So now we have a nice definition of intersection form, so we go back to understanding our definition of the signature. Well, here I have repeated this just as we had it before, so now this part was clear. Now when it was n equals 4k, the signature of the manifold is the signature of the intersection form. How do we compute that? Because that still looks a bit abstract. So what we have to do is to choose a basis for this vector space, this cohomology group, and well, we should try to find an appropriate basis so that when I apply the bilinear pairing lambda to it, then this gives me a matrix which is diagonal. If it isn't diagonal, I can just diagonalize. And when I have my diagonal matrix, I'm just done, because the only thing I have to do is see the eigenvalues and see how many positive eigenvalues I have and how many negatives, and subtract. So then the signature is just found by subtracting the number of negative entries from the number of positive ones. Let's look at an example. So, a very easy one. The signature of this. Well, this is very easy because I will get a tiny matrix, and just because this only has one generator, so my basis is completely straightforward. I only have one of those A's, so only just one, and I know that this polynomial ring is like this. It's just truncated polynomial ring where I'm writing A as the generator. So, well, it's only just one matrix with a matrix with one entry, and I don't have much to say. It's just one entry. If I go to my last part and see, well, found subtracting the number of negative entries from the number of positive ones, I only have one entry, so this is just one. Well, I can think of a more complicated example. So, for example, say that I want to find the signature of this product of projective spaces. Well, and I only have that definition of the signature. I don't know anything else. Well, I would have to think of the generators, and then after a little bit of work and a little bit of diagonalizing and so on, I get to a matrix that looks like this one. So once I get this matrix after quite a little bit of work, then I see, well, I have two positive entries and one negative one, so I have 2 minus 1, so then my signature equals 1. 1 again. But fortunately, we don't have to work through all this from scratch always, because the signature has some very, very nice properties. And if I were to compute this, I would just think that this is 1 and that I have this property here, for example. And it's very nice because it holds for any m and n. So, well, and also to mention here, this property is also this is like that. And this plus here, usually, well, both in Stone and in Milner-Stashev, I think they're referring to it as this joint union of manifolds. It also holds for connected sum. So it's interesting that they only just write sum, but in one first thinks it must be this joint union. It also works for connected sum. And another interesting property of the signature is the third one, that if M is an oriented boundary, this implies that the signature is serial. The proof of this is in Andrew's book. It's also in very, very neatly laid out in well, it has lots of steps in the book by Stone on notes on Cobordism theory. So it's there. And well, this is an important result, that the signature is a Cobordism invariant. So if two manifolds, 4K manifolds, are cobordant, then the signatures are equal. So, just as we saw for the L genus, the signature, when we think of it as a function from the Cobordism groups to the integers, well, it defines this homomorphism. And it's quite clear because once you pick your class, then you apply the signature to it, you get an integer. As we have been computing, these are all integers. And it's very, very important that the signature, just as the L genus did, the signature induces algebra homomorphisms from this tensor product to the rational numbers. So, well, now that we are going to formulate the signature theorem, we should recall that we are thinking about we should recall a little bit about the L genus, and we recall the power series that it belongs to. So this was the power series that it was in 1-1 correspondence to the multiplicative sequence that gives us the L genus. And well, we were denoting Lk as that multiplicative sequence belonging to the power series. So now we can state our signature theorem, and the signature theorem looks like this. Once we have our L genus and we are thinking about how to find the signature of a 4k dimensional manifold, well, it's surprisingly it's a tiny theorem, and it's tiny because you don't need lots and lots of pages to write it, but it's really wonderful because you have that the signature of the manifold equals the L genus of that manifold. Key ideas for the proof. Well, the key ideas for the proof I've already mentioned is that there's the L genus and the signature give rise to this algebra homomorphisms that I have been mentioning. And as these algebra homomorphisms, well, we have them there, to prove the signature theorem, we only have to prove it on the generators. Because once we prove them on the generators, we have proved the Hell theorem. So to prove the signature theorem, we only just have to be sure that this holds. And well, this can be even more simple because we already know that signature of this complex projective space is just 1. So what we have to show is that the L genus, that complex projective space, is 1. So now comes hard work